Okay, hello everyone. Um, Thank you so much for joining me. Um, Today I'm going to take you through um, work, energy, and power. So that's the topic that we are going to look at: work, energy, and power. As you can see from the topic itself, there are three major items that we are going to look at, which is work done, how to calculate work done, and we are also going to look at energy. What is energy, and how is energy conserved, or how is energy transferred within a system or from one object to another object. And we are also going to look at power, and we also calculate power as well. But this is not new to us. This is not strange to us as science students. This is grade 12. We have talked about energy from natural science, grade 7, 8. And we have also talked about energy in grade 10, 11, and now it's grade 12. We are taking it a little bit further. So before I introduce work done in detail, I want you to take you back a little bit to some previous lessons that we have had in our previous grades. So I want to start with what I call interesting facts. And these interesting facts, I'm going to be talking about energy in general. Maybe one learner might be wondering, might be is asking, why specifically look at energy? What's so special about energy? What's so special about work? What's so special about power? Remember, this is science. We try and understand every concept so that we can be able to manipulate it so that we benefit from each and every concept of our life. Right. Now, we were taught previously that energy can be transferred from one object to another, or energy can be transformed from one form to another. Perfect. We need that information also as we move forward. But under interesting facts, I want to bring to your attention that energy is not a concept that we can overlook or we can just rush ourselves. No, energy is an important concept in everyday life. For me to be teaching you like what I'm doing, to be writing, it is because of energy. Right now, I've got light around me, I've got sound, I've got heat. These are different forms or various forms of energy. So, the first interesting fact says energy is an important concept both in physics and in everyday life. That is my first point under interesting facts. So, energy is an important energy is an important concept, all right, both in physics and in everyday life. And in everyday everyday life, right? And energy takes various forms. And energy takes various means different. It takes various forms. Energy exists in different forms, right? And it can be transformed from one form to another, and it can also be transferred from one object to another. So there are two ways that we are dealing with here when we still talk about energy. Energy can be transformed, it can change its form from one form. Like, for example, if I switch on the plug there, I'm converting electrical energy into light energy and heat energy. I did not destroy electrical energy. I simply converted it from electrical energy to light and to heat. So energy can be changed. It can change its form. Then another concept, energy can be transferred from one object to another. We are going to be looking at work done. Now, work done is equals to energy transferred. So when we say we have done work, it means energy has been transferred. Energy can be transferred from the object to the surroundings or from the surroundings to the object. So there are two ways that we must be careful here with: transformed or transferred. Energy can be transformed and it can also be transferred from one object to another. So energy takes various forms. Yes, another point, it says energy, that's what I've been explaining. Energy can be transferred. All right. So energy can be transferred from object to object. Yes, energy can be transferred from one object to another within a system. Within a system. This is a very important point, especially when we are going to look at work done. This is very important. But but changes the face of things, right? But it is never, in as much as we can transfer it, in as much as we can transform it, it is never created, right? Or destroyed. So I'm underlining all the key terms there, right? So we cannot sit down, even when we do our PhDs, we cannot really say we reach a point in life where we can sit down and create energy. Even in the most sophisticated laboratory, we cannot create energy, we cannot destroy. So I think it is very correct for me to make this conclusion for you, uh, which says the total amount, right? The total amount of energy in the universe is always constant. So the total amount of energy in the universe is always constant, is always always constant, right? So what happens on day-to-day life, even in industry, wherever we, how do we keep life going? We do that by transferring energy from one form to another. We keep life going. How? By transforming energy from one form to another and by transferring energy from one object to another. But we cannot create energy. The total amount of energy in the universe is always constant. I want to underline always constant, which means it remains the same. All right. Now, quickly, I want to take you back to these are interesting facts about energy. That the amount of energy in the universe is constant, and energy can be transferred. Energy exists in various forms, and energy is very critical. It's crucial because um, it affects our day-to-day life, even our industry. All right. Now, I want to take you back to what we have done previously, maybe from grade 10 physical science. So I'm going to write a sub topic which says what we already know. What is it that we already know about energy? So what we already know. So this can serve as a quick recap in case someone has forgotten what we have been doing in grade 10. You need to be reminded so that we move together as we move forward. Right now, we are supposed to be calculating or to be using the law of conservation of mechanical energy. You can't do that if you can't remember what is gravitational potential energy. You can't do that if you have also forgotten what is kinetic energy. So we need to be reminded what is gravitational potential energy, how do we calculate it, and what is kinetic energy and how do we calculate it. Then we can move forward and look at other concepts like the work energy theorem and other things. So, what is it that we already know? Number one, we must be reminded about the gravitational potential energy. That is the first thing or the first concept that I'm going to remind you. It is gravitational potential energy. And we know the symbol for gravitational potential energy, it's EP, right? Capital letter E for energy. So I'm saying by definition, gravitational potential energy of an object of an object is defined, right? Is defined as the energy is defined as the energy the object has due or because of its position because of its position in the gravitational field in the in the gravitational field, right, relative to some reference level relative to some reference level. All right, now I want to underline the term reference level. We are doing physics, and this is grade 12. Now, when we normally talk about gravitational potential energy, we take the ground as our reference level. So, in most of our calculations, the ground is our reference level. I'm not saying we are limited to, no, it's not. It is not exclusive to the ground as the reference. But I'm saying in most of our calculations, you must take note that our reference level, it is the ground. Um, is it okay? Now I'm going to show you how we calculate. I'm going to show you how we calculate gravitational potential energy. I'm going to give you the formula, and I'm also going to uh, label the formula so that you know each variable is represented by which letter or by which symbol. So the formula for calculating gravitational potential energy says EP is equals to mgh, right? So if I can put this inside the box, right, I have to identify each letter where your EP, like I said, it represents the gravitational, it represents the gravitational potential energy. Now, we all know from our previous grades that energy is a scalar quantity. What is a scalar quantity? It is a physical quantity that has got only magnitude. It doesn't have direction, right? So energy is a scalar quantity, and it is always measured in joules. So gravitational potential energy, like all the other forms of energy, it is also measured in what? In joules, right? Then your M, when you look at the formula, EP is equals mgh. Your M represents the mass of the object concerned. So this is the mass of the object, and the mass of the object is measured in kilograms. So it means if you are doing a question and they give you mass in grams, you must make sure that you remember to convert grams to kilograms. Then your G there, your G represent the gravitational acceleration, right? So this is the gravitational acceleration, right? And for our gravitational acceleration, for the sake of our calculations at high school, especially the CAP syllabus, we are going to use 9,8 meters per second squared. So that is our gravitational acceleration, and it's a constant. It doesn't change. We don't change it. We keep it. We maintain it like that. If you could check the back page of the question paper, the last pages, there is a table of constants there. You will find G, which is the gravitational acceleration. which is 9,8 meters per second squared. It's acceleration, so it's 9,8 meters per second squared. Then we have got h. Now, what is h? H is the vertical height. Remember, I said we only talk of gravitational potential energy when there is a height, a vertical height between your reference level and where the object is. So your h is the vertical height of the object, vertical height of the vertical height of the object above some reference point. And like I said, and this is measured in meters, right? Like I said, in most of our calculations, we take h as our height from the ground because we normally take the ground as our reference level. So we are saying the height is the vertical height of where the object is from the reference point or the reference level. So this is how we calculate gravitational potential energy. So what it means here is if we are taking the ground as the reference level and the object is on the ground, we cannot talk about gravitational potential energy. That object has got zero gravitational potential energy because the H on your formula there is zero. So it's grounded. It is on its rest position, zero gravitational potential energy as long as it is on the reference level, which is our ground in this case. So we only talk of gravitational potential energy when an object is not on the reference level or it is not on the ground. If the ground is our reference, then we can calculate our gravitational potential energy. EP is equals to mgh, mass of the object, has to be in kilograms. G, that's gravitational acceleration, and then h is the vertical height of the object above the ground or above the reference point. Right. I wish to remind you again, friends, about what is called kinetic energy. Remember, we are doing this prior to work done because we need to be equipped with this knowledge so that we can be able to enjoy our calculations on work done, work energy theorem, and other laws. Right. So now let's quickly look at kinetic energy. So we start by defining kinetic energy, and then we also look at how to calculate kinetic energy. So quickly, my bullet there. What is kinetic energy? I'm defining it now. Um, Kinematics is the study of motion, right? So anything to do with kinematics, it is something that is in motion, which is not stationary or which is not static. So kinetic energy, which is EK, all right, is the energy, all right? It is the energy, it is the energy an object possesses, right? It is the energy an object possesses due to its motion, due to its motion. Now, I want to give you a brief uh, contrast between gravitational potential energy and kinetic energy. Now, we said gravitational potential energy is the energy that an object has due to its position above the ground, and kinetic energy is the energy an object possesses due to its what? Due to its motion. So I want to underline the term motion. So what it means is if the object is not in motion, it means it does not have kinetic it does not have kinetic energy. Now, how do we calculate kinetic energy? EK is equals to half mv squared, right? If I can put this inside there, inside the box. Now let me label the formula whereby your EK, it represents the kinetic energy. It represents the kinetic energy, and this kinetic energy is measured in joules. And then m, it is the mass of the object. It is the mass of the it is the mass of the object, and it is measured in kilograms. Then v is the speed of the object. It is the speed of the it is the speed of the object, right? And it is measured in meters per second, right? So we are saying gravitational potential energy, we have it when an object is lifted above the reference level, right? And kinetic energy is the energy that an object has due to its motion, right? So it means if the object is not in motion, then the object does not have kinetic energy. So if you are standing in one position, we can't talk of kinetic energy because you are not moving. So your velocity is zero. And the moment velocity is zero, it nullifies everything else within that particular formula. So this is how we calculate kinetic energy. And it is very important for me to remind you as learners that we need to make sure that our units are converted to the right SI unit, right? Your mass is supposed to be in kilograms, and the speed or the velocity is supposed to be in meters per second. Now, lastly, let me remind you about a mechanical energy. What is mechanical energy and how do we calculate mechanical energy? Then, with this background now, we can now move on to the gist of the topic, which is work done, energy, and then power. Right. So, what is mechanical energy? So, mechanical energy, which is EMEC, the capital letter M there, the capital letter E, sorry, it's for energy. So, what is mechanical energy? The mechanical energy that an object has, it is the sum total or the summation of its gravitational potential energy and its kinetic energy. Is that okay? All right. So the definition says the mechanical energy, the mechanical energy, which is EM or EMEC of an object, right? Of an object is defined. We need to know the definition of these terms, right? You need to know the definition for gravitational potential energy. You need also to memorize the definition for kinetic energy. So now we are looking at mechanical energy, and you need as well to memorize the definition for mechanical energy and also to state the law of conservation of mechanical energy. Right. So the mechanical energy of an object is defined as the sum. To sum up something, it means you are adding, you put together, is defined as the sum of its gravitational potential energy, sum of its gravitational potential energy, which is EP, and kinetic energy, which is EK. So, in short, we can say EMEC or EM, which is mechanical energy, is the summation of gravitational potential energy, which is EP, plus kinetic energy of the object, which is EK. So this is how we calculate mechanical energy. Right. Now it's up to you now. You can decide to expand the formula if you want, whereby you are going to say EM is equals to, how do we calculate EP? MGH plus, how do we calculate EK? Half MV squared. Now you are enjoying your calculation now. And then the last thing I wish to I remind you, remember, we are still under the subtopic which says what we already know. So we need to be equipped with this information prior to our introduction and our calculation to work done, energy and power as well. So the last thing I wish to remind you, it is about the law of conservation of mechanical energy, right? And you need to memorize it. The law of conservation. To conserve something is to keep constant, to save something. So the law of conservation of mechanical energy. What does it say? All right. So you underline the law there because it's important. It says the law of conservation of mechanical energy says the total. You must also monitor and mind key terms. The total mechanical energy. Remember, science works with terms, so we need to be careful with our terms. So I make sure that I try to underline all the important terms that we need to mind, especially when we write definitions. So the total mechanical energy in an isolated. So isolated, or sometimes you can use closed, right? So you underline isolated. So the total mechanical energy in an isolated system or in a closed system remains constant. Remains constant. When we say it remains constant, it means it stays the same. So let me try to explain a bit here to add some flesh. Now, what are we saying here? We are saying if we can create an isolated system, or if we are having a closed system, the total mechanical energy of an object will be the same, right? And what do we mean when we say isolated? We know from our previous topics that, like momentum, that an isolated or a closed system is a system where we do not have external interference. We don't have other forces interfering with the system. And the chief external force that normally disrupts our closed system, it is frictional force. So we are saying if we can create an environment or a system where we don't have external forces like friction, then that system becomes isolated or closed. It is free from external interference like friction. So we are saying if we have that system, then the total mechanical energy of an object at any given point, it is the same. And remember, when we talk about mechanical energy, we are talking about the summation of EP and EK. So we are saying if ever you pick an object in a closed system at any given point, let's say you have got points A, B, C, right? Or it's a surface where you have got point A, point B, and point C. I am saying if that is an isolated system, there is no friction, and in our exam, how do they indicate that it's an isolated? They don't tell you that it was a closed system. They will tell you that it was a smooth surface, which means it was free from friction. Or they will say it was frictionless, then we know Kuri it's a closed system. And then if we have those 3 points, point A, point B, point C, we are saying if you calculate mechanical energy of that object at point A, and you calculate mechanical energy of the same object at point B, and you calculate mechanical energy of the same object at point C, you must get the same answer because mechanical energy is conserved in a closed system. So you can write it, you can actually have a formula for that. You can derive a formula for that, which says, suppose we have got 2 points in an isolated or a closed, let's say it's an incline or it's just a surface, we can come up with a formula from there. We can say Emac at point A is equals to Emac at point B. So we are saying mechanical energy at point A, which can be any point in a closed system, must be equals to mechanical energy of the same object at another point, which is point B. You can expand this formula. Then how do we calculate Emac at point A? Remember, when you are looking at point A, we must use values at point A. which value is there. Remember, mass is a constant because we are talking about the same object. So I'm talking about the height. We are using height at point A and we are using the speed of the object at point A. Then we get Emac at point A. So how do we calculate Emac at point A? EP plus EK. This is all at point A. This must be equals to EP plus EK also at point B. So this is how mechanical energy is conserved. So we can use this formula, or rather I should say we are going to use this formula. How do we use it and where do we use it? Suppose it's a closed system. You have an object moving from point A to point B. You are given the speed of the object at point A, but they don't give you the speed at point B. And they tell you it's a frictionless, it's a smooth, it's a closed system. Then we know E make at A is equals to E make at B. So the velocity for point A you are given, but you are looking for velocity at point B. So you can further now expand the formula. It becomes EP, how do we calculate EP? It's mgh, right? Plus, how do we calculate EK? Half mv squared. This is at point A. Now, this height is the height at point A. Then this velocity is velocity at point A. Then this is equals to mgh. This new height is the height at point B plus half mv squared. Right, this is all at point B. So height is given, but you are looking for v, which is the velocity at point B. So we can use it as long as it is a closed system, as long as there is no friction there. We can use the law of conservation of mechanical energy. As I close this part for now, I want to emphasize and say we can only use the law of conservation of mechanical energy if it is an isolated system. Now, in the exam, what they normally do is they will ask you, the first question they will ask you or request you to state the law of conservation of mechanical energy. Now, this is a catch. Whenever they request you to state the law of conservation of mechanical energy, what it means to me in my world as a science teacher for the past 10 years, I know definitely the next calculation that follows, they want you to make an application of the law of conservation of mechanical energy, which is Emac at point X is equals to Emac at point Y. But what you must verify before you use that law, just make sure that you read the question carefully and you make sure that it is an isolated system, and then you can be able to use that particular law. So thank you so much for this time that we have had. So what I'm going to do is, for those who are going to catch up in our next video, I'm going to be introducing now work done and do calculations or examples on how do we calculate work done. Thank you so much for joining us. Thank you.